Okay, so welcome everybody to the TAP lecture for the Plasma Initiative. So we're very excited that Professor Anna Tenerani is here visiting us. She's in the physics department at the University of Texas at Austin. Prior to that, I think she joined the faculty in 2019 there, right?
Yeah.
And prior to that, she was in the Los Angeles area, first as a Caltech postdoc at the Jet Propulsion Laboratory, and then sort of made a lateral move over to UCLA, where she took a research scientist position before going to Texas. She is an expert in plasma physics, one of the leading experts in sort of nonlinear dynamics of plasmas, especially collision-less plasmas, where collisions don't play a major role, like with the most prime example being the solar wind. Formation of plasma instabilities, their importance in heating the plasma and also in magnetic reconnection. So the primary application, so she's involved in the Parker Solar Probe mission. Are you co-I?
No.
No, okay. Sorry, I wasn't exactly sure about that.
Just study.
You just well, I see you at a lot of Parker Solar Probe meetings, so heavily involved in Parker Solar Probe, which is making these very close passes of the sun and telling us all sorts of new things about how some of the big questions that we're facing is, why is this solar corona so hot? Why, what accelerates the solar wind? Things like this. And you really need to get under the hood and get at the details. And this is what Anna does, and she's an expert at this. So thank you very much for coming here. Let's welcome Anna.
Thank you. Thanks for the very kind and generous introduction. And I also want to thank in general the TAP committee for extending the invitation to come here. And it's been great to visit in Tucson. Okay, let's get started. Yeah. So I have divided this lecture in two blocks. So in the first part, I will give a general overview on the main science questions I'm going to focus on, as Joe has already mentioned, coronal heating and solar wind acceleration. And after all, since this is the Plasma Initiative, I also have a couple of slides just to give you a flavor of plasma physics, and what are some challenges that we face when studying plasmas, just to make sure that we are all on the same page. Then in the second part, I will show some key features observed by the mission Parker Solar Probe, and I will highlight some selected work I've done in the context of this mission. And then I will conclude with one slide of summary and open questions. And please feel free to interrupt me. I would rather not get to the end of the talk, but that you understand. I just don't lose you along the way. All right, so I'm sure that y'all are familiar with this kind of images. This is an image of the solar corona during a total solar eclipse. And I like this one particularly because it shows in great details all of the structures. There are these rays coming from the poles, and then this elongated structure, these elongated loops or streamers, which are the imprints of the coronal magnetic field. So the solar corona, which is the outermost layer of the solar atmosphere, is made of a gas at temperatures in excess of 1 million degrees. And because at those temperatures, the gas is ionized, the corona is made of a magnetized plasma. And this plasma is not confined, but it expands in interplanetary space through the solar wind, which is literally a wind of particles, mostly electrons and protons, which create our own heliosphere. And this sequence of images here have been taken with a spaceborne coronagraph, and you can see this continuous outflow of material, which is the solar wind. And despite much progress has been done, why the corona is so hot and how is the solar wind formed in the first place and accelerated still remain fundamental open science questions, and they're fundamental component of space physics and arguably also in astrophysics. Now, what I want to stress here is that coronal heating, solar wind acceleration, and in general, all of the solar activity is the result of interactions of particles with electromagnetic fields, which give rise to complex nonlinear plasma dynamics, to mention a few: turbulence, formation of waves, instabilities, wave-particle interactions. And so plasma physics is really a fundamental component to space physics. So at this point, before continuing on the topic of coronal heating and solar wind acceleration, let me take a pause, okay, and give you a general broad overview of plasmas. So this is my one slide plasma in a nutshell. And I apologize if you already know this, but. So what is a plasma? A plasma is an ensemble of electrically charged particles that interact as a collective system via the self-consistent mean electric and magnetic fields. So what does it mean that they interact as a collective system? So for example, they give rise to phenomena like waves. So in many ways, plasmas are similar to fluids and behave like fluids. Propagation of waves is just one example. However, plasma are different in at least two fundamental ways with respect to standard fluids or neutral gases. First, a neutral gas doesn't care if there is a magnetic field or not. On the contrary, charged particles are free to move along magnetic field lines, but they are bound to gyrate around magnetic field lines. So what that means is that in a plasma, you can have dynamics at spatial and temporal scales on the order of this gyro motion. But you can also have dynamics at scales much larger than that. And so plasma dynamics is intrinsically multi-scale. And so this poses challenges for numerical codes, for example. The other fundamental and crucial difference is that while in a standard gas, the hotter it is, the more it collides, the opposite happens in a plasma. The plasma, the more it is hot, the less it collides. And precisely, the collisional frequency scales as the inverse of the temperature to the 3/2. And so this poses a problem, because then how are you going to heat a plasma if the more you try to increase the temperature, the less the constituent particles are colliding? So what that means is that your traditional ohmic heating or Joule heating, however you want to call it, is inefficient in high temperature plasmas, dilute and high temperature plasmas. And other mechanisms must come into play to heat the plasma, such as wave particle interactions. The other implication of this strange behavior, which, by the way, is related to the fact that charged particles interact through the Coulomb force, is that in the vast majority of astrophysical plasmas, the environments are essentially collisionless. So the plasma is collisionless or extremely weakly collisional, and therefore they are often found out of thermal equilibrium. And even the definition of temperature is really not well posed. So how do you deal with this kind of system? How do you describe plasmas? Well, it depends. That's it. That's kind of the answer. So you can have, on the one hand, the microscopic description, the kinetic description, which, and in this framework, you describe the plasma as a statistical system through the distribution function f of particles, which obey this kind of equation. Here on the left-hand side, essentially, you have advection in phase space, and on the right-hand side, this here represents the collisional operator. And this kind of description allows you to study really the dynamics out of thermal equilibrium, like I said. It allows also to study the formation of accelerated population of particles, like beams, or it allows you to study wave particle interactions. This kind of description, however, contains a lot of information and sometimes even more than what we actually need. And sometimes it also lacks some physical intuition because we are more used to think in terms of macroscopic quantities like density, bulk velocity, pressure. And so the other possible description of plasma is the fluid macroscopic description, which relies on the evolution equations for these macroscopic quantities, density, bulk velocity, etc. Now, there are a ton of caveats that go into the validity of using a fluid description in a collisionless plasma. And in principle, they should not work. However, they work surprisingly well to describe phenomena that are fluid in character, like propagation of waves, the turbulent cascade, the formation of thin boundary layers, to give a few examples. So in this lecture here, I'm going to consider the fluid description of plasmas in what follows. All right.
So just real quick, when you say fluid description, the quantities you have on the right could still be separated into different species, or
Yes,
can you combine them
that's
into
right.
one species now? Okay.
Yeah, that's right. So you could have multi-fluid,
Yeah.
multi-species, and then it depends also on the scales of the dynamics you are interested in. And if you are, in fact, at the very large scales, when I say very large here, I mean larger than intrinsic proton scales, like the gyro radius, then you can describe the plasma as a whole highly conducting fluid, which is in fact the description I'm going to adopt, which is the MHD description.
Quick question. In the work that you're about to describe, you're just assuming Maxwellian velocity distribution function?
Sorry, could you say that again?
In the work you're about to describe, are you just assuming a Maxwellian velocity distribution function?
Yeah, I mean, once you accept the free description I'm gonna adopt, which is MHD, you are assuming Maxwellian and also collisional technically.
So you're talking about like isotropic pressure. Is that what you're referring to?
Yeah. Although, right, that's a specific model. You could have fluid models that allow you anisotropic pressures. So there is a plethora of of fluid models that are developed exactly to improve physical accuracy. Other questions? So, by the way, yeah, locally Maxwellian. Yes. Okay, so going back to the our business. So what do we mean by coronal heating problem? So here I'm showing the profile of the temperature as a function of the height above the photosphere. And in this plot, I've also indicated some commonly used spectral line to study the solar atmosphere. Now we know that all of the heat that we receive from the sun comes from the nuclear reactions that take place at the core of the sun. So we expect that as we move away from the center, the temperature should decrease. And this is what happens initially here. This is we are at the boundary of the photosphere. Then there is this little bump, and so this is very comforting because this is what we expect. And then there is this little bump here. This is the chromosphere. But then something very strange and unexpected happens. There is this thin region, which is called the transition region, in which the temperature jumps up of more than 2 orders of magnitude. And this is where you have the corona. So this is completely unexpected and counterintuitive because if you allow me an analogy, is like imagining a pot of boiling water on top of a piece of ice. So the question arises, how is it possible that we can maintain these extremely high temperatures on top of a much cooler body steadily? And so this is in a few words, the coronal heating problem. Now, we know that there is enough energy stored in the magnetic fields to power the corona. So the problem really is to understand how specifically the energy stored in the magnetic field can be conveyed to the plasma itself. And so there are different scenarios, and usually we have two culprits: magnetic field reconnection and turbulence. And in the in this lecture, I'm going to focus on the turbulence perspective.
Can I ask a question?
Yeah.
This figure, sorry to keep it.
No, please.
So this is temperature versus height, but is this treating the sun like a star, and you're just because I think if I look at an X-ray image of the sun, there's bright spots and
Right.
dark spots. So does that profile represent the average of the entire sun, or is it?
No, it represents each layer essentially. So depending on the wavelength you look at, so for example, if you look in the extreme ultraviolets or in the X-rays, you will see the hottest regions here, and then
I guess what I'm saying is the temperature is a function of both
Oh.
radius and latitude and longitude as well.
I see.
If you're above an active region on the sun.
Yes. And specifically, also, this was taken from a paper where this profile was extrapolated for a corona hole.
Oh, okay, so these are the dark X-ray spots on the sun. Darker, the corona.
But yeah, I mean, you're right. Or let's say smoothed out of all fine structures. Okay, so this is also the region where the solar wind is formed. And in fact, because of these very high temperatures, the plasma has enough kinetic energy to escape from the gravitational attraction of the sun. So understanding what forms and accelerates the solar wind is intrinsically related to understanding what hits the solar corona. And the two problems are really two faces of the same medal. Now, the first person who predicted the existence of the solar wind based on this argument was Parker in 1988, starting from the set of steady-state hydrodynamic equations here. So what this equation, the first equation here, represents the continuity of mass in spherical geometry. And the equation below is the momentum equation. Here, U is the flow velocity, assumed to be radial. R is the radial distance from the sun, rho is the mass density, P the pressure, G represents the gravitational attraction of the sun, and C is the sound speed. So here we assume, here there are not even magnetic fields. This is really hydro, pure hydro. And it is assumed that the plasma is isothermal in this particular case. And you can have fun and solve these equations. And what you will find is different classes of solutions. And Parker argued that the only physically acceptable solution is the one corresponding to the transonic wind, which is a wind that is continually accelerating out to becoming supersonic. The reason why I argued it was the only physically acceptable solution is because it is the only one that matches a nearly zero pressure. It has zero pressure at infinity, and so it will be the only one that matches the extremely low pressure in the interstellar medium. And this graph here is taken from his paper, represents a family of these transonic solutions. On the y-axis, you have the flow velocity in kilometers per second, and on the x-axis, the normalized radius, normalized radial distance from the sun, normalized to the solar radius. And each curve is a solution obtained imposing a different temperature at the coronal base. Now, at that time, there was still a debate on whether a supersonic wind existed or not. But just 1 year after this paper came out, the solar wind was actually measured in situ, first by the Russian, by mistake, actually. They wanted to send a probe on the moon, but they missed the moon. And then by the United States, I believe with the Mariner mission.
Mariner 2, maybe?
Yeah. And so there you go. You have your supersonic solar wind as predicted. So the theory of Parker is beautiful in its simplicity, and it kind of get it kind of right. But it fails to explain details that we observe. So this plot, so this image is a composite image. And what's shown here is a polar plot of the measured velocity of the solar wind in situ by a mission, Ulysses, that was alive in the 90s. And this is so far the only mission in near the polar orbit around the sun. So this polar plot, in fact, is the result of multiple years of measurements that took to complete one orbit. The color blue and red represent the dominant polarity of the magnetic field, outward or inward. And then this is superposed to a snapshot in time of a composite image taken from a white light coronagraph and EUV emissions. And so this superposition has been done for the sole scope to guide the eye in making connections, qualitative connections, between wind structures and magnetic field structures. So what became clear with this mission, Ulysses, and this is the typical configuration that you get at minimum of the solar cycle, so that you have wind structures and magnetic field structure organized in an orderly way. So what became clear with this mission is that you generally have, at minimum of solar activity, a highly variable slowish wind at the lowest latitudes. The speed will range between 200 to 400 kilometers per second in correspondence of closed magnetic field lines. And then at the higher latitudes, you have a relatively steady, fast wind that reaches speeds up to 800 kilometers per second, coming from coronal holes. So coronal holes are those regions where the magnetic field lines are open, in a sense that they stretch out in interplanetary space. Okay, so, and here we start to have problems because the theory of Parker didn't predict the existence of different types of wind. And instead, one thing that this points out is that depending on the type of magnetic structures and in fact of magnetic topology that you have in the corona, you get a different type of wind. It determines the type of wind that you get. The relatively steady wind coming from the Parker model really resembles more the wind coming from the coronal holes. The problem is that this wind is too fast, and the Parker's model cannot predict speeds up to 800 kilometers per second like those that we observe. So even in this case, there has to be some missing element, some missing ingredient mechanism that allows to give the wind an extra kick so that it can accelerate to the speed that we actually observe. So this is, in broad terms, the acceleration problem of the solar wind. Now, if you think about it, the wind predicted by Parker is laminar. In fact, it was in my title in the previous slide. It's laminar in the sense that it is supposed to be smooth with well-defined streamlines pointing radially away. But what we observe, in fact, is that the solar wind is not laminar. It is, in fact, permeated by large amplitude fluctuations, and these oscillations that you can see here in the fast wind, in fact, are oscillations in both the velocity and the magnetic field. So one of the ideas is that it is these waves of fluctuations that provide that mechanism that can both heat the plasma and accelerate the solar wind. And I'm going to show you in a couple of slides how this would work. And in support to this idea is the ubiquitous observations of fluctuations in the solar wind. And this is a beautiful example of the spectrum of magnetic field fluctuations at one astronomical unit. Generally, what we find is that there is a low frequency range, the one shaded in blue, that scales with the frequency as the frequency to the -1. This is referred to as the energy containing range, and people are still people are working to understand what's the origin of this specific slope here. Then what follows is a range of frequencies that's called the inertial range. And this is analogous to the inertial range of turbulence coming from is analogous to the inertial range turbulence of the phenomenological theory of Kolmogorov for fluid turbulence. But in a fluid, what happens is that when you arrive at the dissipation range, then there is the sink for your turbulent cascade. You start to dissipate, and that's how your spectrum ends. In a plasma, instead, you reach the intrinsic proton scales, like the Larmor radius, and then the energy cascade continues into a so-called sub-inertial range. And here is where we think that wave-particle interactions might come into play to provide that sink of energy, terminating the cascade, the turbulent cascade, and ultimately heating the plasma. Now, look at the range of frequencies spanned by the fluctuations in the solar wind. It's like 8 orders of magnitude, or something like that. So there is no way that you can simulate this with direct simulations. On top of that, this is what we observe at 1 astronomical unit. But these fluctuations have been supposedly generated back, to the sun and have propagated all the way there. And so in principle, you have to account also for expansion effect. So you have to account for the fact that this spectrum has evolved from the sun all the way to the Earth. So understanding turbulence in the solar wind is a super multi-scale problem. And in fact, it is. Understanding how this works is really one of the largest research areas in the field. The focus of this talk will be specifically on fluctuations at the largest scales. Like I said, what that means is that they are larger than the Larmor range. So we are in this inertia, between this energy containing and inertial range. So I'll show you the spectrum. The existence of a spectrum is a symptom of a turbulent cascade, so nonlinearity is at play. Now, if we take a look at how the waveform of this fluctuations looks like.
The solar rotation, is the solar rotation rate on?
No.
Rotation frequency is way to the left?
Yeah.
Okay, so this doesn't cover the rotation.
Yes.
Oh.
Okay. So here is, like I said, we have a spectrum. How does what these fluctuations look like? And this is one of the first observations of waves in the solar wind. And what it's showing is fluctuations in the velocity and the magnetic field in 3 orthogonal components. And so for each component, you see that there are 2 lines, okay, one for the velocity, one for the magnetic field. And what is remarkable is that the velocity and magnetic field fluctuations are almost perfectly superposed. So this is the clear signature of a type of wave that's called Alfvén waves. And I'm going to explain Alfvén waves in a few slides. And the fact that, in fact, you can describe these fluctuations as well-defined waves poses a challenge at a fundamental level to the traditional theories of turbulence. But in any event, there is ample evidence that these fluctuations are ubiquitous, and so there is a class of models that try to incorporate the effect of these fluctuations on the solar wind, which are called wave-driven wind models. So these are an example of the starting equations for this model, and they are an upgraded version of the hydrodynamic equations I showed you earlier. And they are an upgrade in 2 ways. One, now we are including the magnetic force. The J cross B is buried in here. And two, you are accounting for the effect of fluctuation represented by these delta quantities. And these equations have been derived after a two-scale analysis, by assuming that you have a steady state average wind, and then on top of that, you have rapidly varying fluctuations, and you are averaging, and you are taking the average of it. So the bracket denote the average over fast time and spatial scales. So if these fluctuations are large enough, you cannot neglect them, and they contribute to the average wind. And in particular, they can accelerate the wind through Reynolds stresses and magnetic pressure, wave pressure. And by dissipating, they can also heat. Now, this last equation, some of you are kind of screaming in their head. This is the simplest possible equation you can write for the temperature. So to describe the radial evolution of temperature. And on the right-hand side, you have the first term. The first term represents adiabatic expansion. So just simply by the fact that the plasma is expanding spherically, it cools down. And so that's the first term here. And the second term is a source term. And I have introduced this parameter epsilon, which has the dimension of a heating rate per unit mass. And this is really like a Pandora's box or a black box where we hide everything that we do not know or that we cannot describe with the fluid model. Now, in this specific kind of models, wave-driven models, this epsilon really represents the heating rate due to the dissipation of fluctuations. So at the core of the issue is to understand how these fluctuations evolve from close to the sun all the way out, and how much is this epsilon. So to understand if these fluctuations can actually do the job to heat the plasma and accelerate the solar wind, it is necessary that we investigate how these fluctuations look like, and it is necessary to calculate this epsilon as close as possible to the sun. Yeah.
I don't want to give you out of order. I don't understand what the dissipative mechanism is.
The dissipate. Oh,
Maybe
yeah, that's a good question.
the plasma should carry the alpha waves. How do they turn into heat?
Right. So, at the end of the day, you have to form small scales, small enough that you can trigger phenomena that dissipate the wave. Okay. There are different ways in which this can happen. So the turbulent cascade, for example, is a way in which you start to inject energy at larger scales, and then by nonlinearities, the energy is transferred towards smaller and smaller scale, until you achieve small enough scales that then the collisions cannot be neglected anymore. Okay, from a kinetics perspective, you need to have phenomena that create filamentation in phase space, like small scales, essentially, strong gradients. And then at that point, collisions cannot be neglected and will do their job.
But for this presentation, you're just going to say, I've abstracted that all away, and there is a dissipation, and we just put a constant.
Right.
Okay.
Yeah. So in most cases, well, you could also include like a Joule heating, okay? And you can make this more and more, sophisticated. But the state of the art basically is that because you cannot do a self-consistent global simulation to figure out how things work, you have to separate. You have to either include fluctuations phenomenologically, or you prescribe a flow profile and study the evolution of fluctuations on a prescribed flow profile. So that's why ideally we want a model that is consistent with observations that allow us to really insert this correctly into the average wind.
So, but the heating, to kind of go along with that question, that epsilon is kind of, I guess, in some sense, so in the equations that you wrote down to obtain these, is there like a resistivity kind of term that shows up that's wrapped up in there somehow? Because like if you write down like the proton momentum equation, the electron momentum equation, I guess there's got to be some way to
Okay.
exchange between the two, and there's some sort of resistivity, I guess. And is that what this is? Is this term related to that? Because if you have,
Sort of, but it's subgrid in some sense.
because if you have ideal MHD, for example.
Yeah.
There's no resistive term, right? So you wouldn't necessarily get I don't think you would get a dissipation, right?
Okay. If you did a simulation of local simulation of turbulence, for example, well, to have dissipation, you have to have your explicit resistivity. But you can, okay. But here you are representing the effect of fluctuations as a subgrid phenomenon.
But let me
Okay,
put
so-
that in different words, and you can see if I've got it. It's not really resistivity because you're assuming it's a collision with plasma.
Yeah.
So what you're instead assuming is that if you could track the velocity distribution function down at the sub-Larmor radius scale,
Mm-hmm.
that you would find that there is a mechanism in which alpha waves do not transmit themselves without dissipation,
Yes.
but they convert their
Well-
motion through a non-collisional process
Ultimately, to have
heating
heating,
down in the.
you have to increase the entropy. So you have to have collisions.
Okay,
So this is probably one of the non-LTE questions, the difference between heating and removal of energy from the fluctuations.
So ultimately, you have to have collisions. Okay, that's the sink. But the rate at which this the rate at which this happen, in fact, is dictated by the ideal dynamics. That's at the heart of the concept of the turbulent cascade. So the rate at which this energy is being dissipated, it will be dissipated because of dissipation, but the rate at which it dissipates does not depend on collisions. Okay, and in fact, this epsilon here, in principle, you could calculate it. I mean, based on models from the amplitude of fluctuations themselves. So and this is model dependent. That's why all of this is very delicate. But you can calculate from the data this heating rate by looking at correlation of specific functions of the amplitudes and spit out a number there.
But
I'm
not,
gonna ask one more and then I'll shut
Yeah.
up.
No. I hope I don't know, I answer.
But the distribution of at least electron energies in the solar wind, even at macroscopic scales, is not Maxwellian. So I don't understand how we can say all of the interesting physics that's causing this phenomenon must disappear down at the sub-Larmor radius scale, because we observe macroscopically that the thermal velocity distribution functions are not Maxwellian even at large scale.
What do you mean? What do you mean?
And there's a big tail. There's this big
Once you-
population of fast electrons in the solar wind.
Right. So what I do not understand is, so I look at distribution functions. What do you say? Well, that's like a local measurement. So I don't understand that. Why do you say that this is a global?
Because the distribution of energies of electrons that we observe macroscopically at large scales in the solar wind, the population of electrons of various velocities does not follow a Maxwellian distribution.
On that, I agree.
So something is happening,
Mm-hmm.
which is not captured by sub-Larmor radius processes, because there's this long tail of high energy particles that is present even when you average over large spatial scales.
Okay. Yeah.
So I'm not understanding how you can capture the physics by saying all the non-equilibrium stuff is down at the sub-Larmor
No, you
radius
say
scale.
that.
Okay, that's okay.
Right,
Carry on.
And yeah, I mean, maybe this was not a good idea, but
I think
so just let me, otherwise I lose my thought. For example, the fact that you have this long, tails in the electron distribution function, what that means is that there is a heat flux. So you will have to include that in here. So, so that also contributes to, how you transport the, how the temperature evolves with radial distance. It depends on heat fluxes as well. And those, the more you are, and those depend on the details of the distribution function of particles. So there are ways to incorporate these non-thermal effects into global models. Yes.
all I was gonna say was that in the equations, not these, but the ones before where you were talking about the fluid approach and the macroscopic
Yeah.
approach that you called it. The F doesn't, it doesn't have to be Maxwellian. In other words, well, that's why I brought up the pressure. If it's a Maxwellian, then you're gonna have an isotropic pressure. You could have a Maxwellian with two different, the temperatures in different directions or something like that. The random motions to be in different directions, and that's fine. But you can have an arbitrary distribution function and put it in and get the same equations, actually. It's just the pressure tensor might
Yes.
look a little different.
The problem
and the
is,
flux will look a little
the
different.
problem is that, how do you close your chain
Yes, right.
of fluid equations?
But I kind of want to get away from the Maxwellian. It doesn't have to. In other words, many of the equations will look the same, even if you have
Yeah.
a non-Maxwellian F.
Problems begin with the pressure.
Yeah, right. And Q.
Pressure
and the heat flux,
tensor.
Right.
And starting from the pressure tensor, then it follows, and so, right. Simplest thing you do, okay, is say isotropic. That's your MHD. Then you say, okay, it's an isotropic, then you have other models, CGR, but still you don't include the heat fluxes. And there is a zoology, I think, of models that try to include, but I mean, you're asking like these questions doesn't motivate research essentially in this field. So there are attempts to incorporate not necessarily microscopic, but kinetic effects into a macro, fluid-like description, which certainly is not here, but that could be. I could provide a better example. Yes. Okay. So to answer all of these questions, at the end of the day, okay, here we are. NASA launched the mission Parker Solar Probe in 2018, exactly to understand what hits the solar corona, what accelerates the solar wind, and explore mechanisms that accelerate and transport energetic particles. And this lecture is really built around the first two science objectives of this mission. And this is the orbit of the probe from its launch until 2 days ago in green, and in red is the future orbit. So far it has performed 21 orbits out of 24. And as you can see, the perihelion shrinks with time. This is thanks to Venus gravity axis, during which the probe folds a little bit towards the sun until the probe will achieve the closest of the approaches. This Christmas Eve here, the distance achieved will be within 10 solar radii. So what I do want to point out is that before Parker, the closest spacecraft to the sun was the Helios mission, which arrived to the orbit of Mercury. And so until now, we had knowledge gap of the state of the plasma within the orbit of Mercury. And Parker Solar Probe is helping us to fill this gap. But before I show you the key features, okay, this is okay.
Oh.
And I think it's of interest to astrophysics in general because Alfvén waves are a fundamental type of oscillation that you have anytime you have a magnetized plasma. These are large scales, again, scales larger than Larmor radius. They are driven by magnetic tension and inertia, and they propagate along a mean field that I will call B naught here at the Alfvén speed. The Alfvén speed is defined as B naught divided, I'm using CGS units, divided by the square root of 4 pi rho, and rho is the mass density. The characteristic of this waves is that the velocity fluctuation and the magnetic field fluctuations are perfectly correlated or anti-correlated, parallel or anti-parallel with this specific relation of amplitude. And so they're very easy to spot in observations. Now this is the cartoon, and I guess this was just the equation version of it. I think I can skip this one because I only have 15 minutes left. But I'm actually going through this. Okay, so what I have here, these are the MHD equations that we were talking about. So the first equation is the momentum equation. And in addition to the pressure forces, now you have the J cross B, which appears now in the form of magnetic tension here and magnetic pressure. The second equation comes from Faraday's law of induction, from Maxwell's equation, and you neglect displacement current, and then you assume a ideal Ohm's law. So you represent the plasma as a perfectly conducting fluid, and you get this evolution equation for the magnetic field. Now, for the sake of argument, let's say that the fluctuations are incompressible, so this term goes to 0. And let's also say that both the pressure and thermal pressure and the magnetic pressure, this B squared, is constant. So this term also goes to 0. Then I can combine these two equations. I can sum and subtract them. And then I can introduce these new variables. Instead of U and B, I have Z plus and Z minus. So when I do that, I end up with an evolution equation for Z plus and Z minus. So if you have an Alfvén wave, you have perfectly correlated velocity and magnetic field fluctuations. So what that means is that either Z plus or Z minus are exactly 0. So in that case, this last term goes away. And here is the problem, because this is the only term that allows you for the nonlinear turbulent cascade. And in the solar wind, to lowest order, this term is really, really almost 0. And so when you neglect this term, you just end up with an advection equation for these fields, Z plus and Z minus. So Z plus and Z minus each represent Alfvén waves propagating parallel or anti-parallel, respectively, to the mean field. And they are also advected by a mean flow if it exists. And what all of this means is that purely correlated or anti-correlated velocity and magnetic field fluctuations with constant magnetic field strength and pressure provide an exact solution at any arbitrary amplitude. So these don't need to be small amplitude waves, can be very large, of the nonlinear compressible magnetohydrodynamic system. I say compressible because if U and B are correlated, then the divergence of U is 0 automatically. So this is all nice. It seems like just a mere example, but it is important because this is exactly what we observe in the solar wind. And this data show the magnetic field measurements of the radial component of the magnetic field during the first orbit of Parker's solar probe. This is one of the most beautiful things I've ever seen. What you can see, there is an envelope here, a baseline magnetic field. And this is essentially the magnetic field that you expect from textbook that scales as the inverse radial distance squared, okay? If you have a radial magnetic field in spherical geometry, that's how it should depend with radial distance. So this envelope is exactly that. So you have your inbound portion of the orbit, so the the spacecraft is moving closer and closer, so the intensity increases of the baseline magnetic field, and then it goes through the outbound phase and goes away, and intensity decreases. All good, and now on top of this baseline magnetic field, you have these gigantic spikes. These gigantic spikes are large amplitude Alfvén waves. These are similar to the Alfvén waves that we observed and we saw at 1 astronomical unit a few slides back. But because we are closer to the sun, the intensity of the magnetic field is so much stronger and the amplitude of the fluctuations is so much larger that they stand out like, whoa, what's going on? And sometimes these fluctuations are so big that the magnetic field flips a sign momentarily. So you have the magnetic field pointing one way, and then what happens during the spikes is that it flips back before going back to its original position. And because the sign changes of the magnetic field, the biggest spikes here are called switchbacks. So what Parker Solar Probe is telling us is that the near-sun solar wind is permeated everywhere all the time by these gigantic Alfvénic fluctuations. And these Alfvénic fluctuations, including switchbacks, are the turbulence of the solar wind. And this is a close-up view of a canonical switchback. The top plot shows the radial magnetic field that drops back from positive to negative values, and then it goes up again. In red here is the strength of the total magnetic field, which if you think about how big these fluctuations are, the delta B over B is 1. The magnetic field remains like, the strength of the magnetic field remains flat. That's pretty remarkable, and that's an important property that still we haven't really figured out yet. And the signature of a magnetic switchback in the velocity field is that of a radial jet, reported in this bottom plot. Now, to tell you the truth, in retrospective, switchbacks are observed also far from the sun, but never in such a prominent and kind of striking way as Parker Solar Probe showed us. But there are signatures that are unique to the near-sun environment. And this is the fact that switchbacks come into patches, into groups. This is another example of data taken during the 10th encounter of Parker Solar Probe. The top black line shows the radial component of the velocity. The blue line, we don't really care here, but is the relative abundance of alpha particles. And then the middle panel in black is the radial component of the magnetic field. So you can see the same features here of these spikes. These are all switchbacks, and then you have all of these radial jets correspondingly. And the switchbacks come in groups, in patches. So you have a group of switchbacks denoted marked by these red lines, and then you have a relatively quiet period, and then you have another burst, and then a quiet period, and then another burst. And so in a recent paper, it was shown that these patches are consistent with the supergranulation scale structure at the coronal base. And these signatures are in fact washed out as we move further away from the sun. So this is really something that Parker Solar Probe has allowed us to see that was not obvious before. And so one of the ideas is that maybe these signatures, is the fact that come into patches and that correlate with the supergranulation, are telling us that these are the imprints, maybe, of how the solar wind is formed in the first place. So at this point, there are, however, more questions than answers. Okay, so I don't think I'm going to make it. So I have 5 minutes, maybe, but I should just maybe just go through the next slide and probably conclude. So, like I said, we have more questions than answers at this point. In general, about fluctuations still in the solar wind, but also specifically now about switchbacks, given what Parker Solar Probe is showing us. And so, of course, one set of questions is, where do they come from? And there are 2 schools of thoughts. a line of thought places the origin of switchbacks back in the corona. And what they're claiming is that reconnection between open and closed field lines generate the switchbacks. And so in this case, switchbacks are just a proxy or a byproduct of reconnection, which will be the actual, responsible for generating the wind. And then in the other school of thought, instead, switchbacks are generated dynamically as they evolve in the solar wind. They could be generated through underlying shear flows that will drag magnetic field lines and form switchbacks. Or you can start with a bath of turbulent fluctuations, and then the expansion drives the formation of switchbacks automatically. So this is, the set of questions of their origin. But then there is also the question, okay, once they're formed, how do they evolve in the solar wind? And this is really the aspect I've been more, focusing on in my work. And answering this question, in fact, can help us understand their role in the turbulent cascade, in heating, and can also understanding their stability properties. For example, can place constraints on possible origin mechanisms. So very briefly, for example, along these lines, the work I've done has shown that, I'm going to show you just a simulation, okay, of a simulated switchback. One of the questions that we had is, these are very large Alfvén waves, and what is known is that when the amplitude is very large, these waves are unstable, and they decay due to parametric decay instability. This process is really, in its simplest version, a three-wave resonant process where you have a pump wave that resonates with a back-scattered lower frequency wave, and then a forward sound wave. And so the question is, these switchbacks are gigantic in amplitude, so can they be generated in the corona, and are they stable enough so that they can propagate long enough that we can observe them? So that was kind of the motivation for doing these simulations. And so here, this is the simulation domain, and the black lines represent magnetic field lines so that they kink. And the color code represents density fluctuations. And so you can see that this thing is relatively stable, but sooner or later it starts to interact with these density fluctuations until it unfolds completely. And so what we learned from this work, in fact, is that the rate at which this process happens, at which the wave packets decay, is strongly dependent on the volume filling ratio of your wave packet. So basically how wide it is with respect to your domain and on boundary conditions. So to understand this, with a student of mine, we did a semi-analytical work to calculate the decay rate for different volume filling ratios and different boundary conditions. So in this case, open boundary conditions would represent the quietest wind, where you have no perturbations downstream your kink, whereas periodic boundary conditions represent the most unstable one, where you have the same kind of perturbation hitting always with the same phase your kink. And so this lends to be the most unstable case. But I guess the point is that you can have a range of possible decay rate. And so one of the conclusions is that, in the worst case scenarios, switchbacks can decay pretty rapidly depending on wind conditions, but they can also, if the conditions are good, propagate long enough for them to be observed. So while it is reasonable that they can be generated dynamically in situ, like some are claiming, it's also possible that it's not to be excluded that they are generated in the corona. And in fact, likely different types of switchbacks can coexist. All right, so this was a summary and conclusions for you, but I wanted actually to show you pictures from Austin. We had a rare aurora. I didn't see that. I took it online. And this is a photo that a student of my colleague actually took with an iPhone during the total eclipse. Yeah. And thank you
Right.
very much.
Okay, so very interesting. We're kind of right at the hour now, but
No, thanks.
certainly we had quite a few questions during the talk, but anybody have a question right now?
If you don't mind going back to the slide where you have the turbulent spectrum. Just a question.
And this?
Yeah, so spacecraft frequency, what the heck is that?
Was sorry?
Spacecraft frequency, I was just curious what is that?
Why they wrote spacecraft? It's just the, you know, the in the spacecraft frame. I mean, the spacecraft is measuring time dependent.
Okay, yeah, that makes more sense. Okay, I was like, something about the instrumentation. Okay.
Yeah.
It makes more sense if it's just the way.
No, I believe that that's just the.
Just frequency is probably
Yeah.
better. It's less confusing.
Well, I'll send it to you now.
I don't think there's any time dilation or
Yeah,
anything like this.
But there hasn't been a Doppler shift applied, right?
Oh,
That's
okay.
why they
Yeah.
added that adjective there.
My shape functions or delta.
So because then they translated that into scales up here.
Is there, I saw another question.
I'm not sure at this distance is usually the Doppler shifts or are not.
Yeah,
It's like
Taylor
this,
is
so-
pretty well applied here.
Yes.
Just wondering how long into the next cycle Parker will be observing and see if switchbacks change with.
Right. So there's going to be an extended mission, though I don't know for how many years. It's been.
We're writing that right now. So, right, so it launched in 18. And so the first 4 years were a lot of minima. We're seeing a lot of the maxima right now. And we're hoping at least for one, if not more extensions.
So one question maybe related to this, you showed Ulysses plots early on, right? You don't have to show it again, but yeah, there were no obvious switchbacks in these plots,
Yes.
right?
Yes, there are
So-
actually.
Yeah, but they're not quite as apparent as they
No,
are in the
that's-
Parker solar probe.
No, that's true.
So
Because
so my question is, if you are in polar coronal hole material, which sometimes happens at low latitudes, do you see fewer switchbacks or more switchbacks, or does it tell you anything about that?
okay, so
Is
essentially.
it a radial distance issue, or, you know, what?
No, okay, the reason why that, when you look at Parker, it's like a whoa. It's
Yeah.
because you're closer to the sun and everything is stronger. And when you are, you know, further away, the magnetic field is weaker, relative amplitudes are larger, but in absolute values, everything is just weaker. So they're less impressive. But in fact, any wind that comes from coronal holes is galvanic and it has switchbacks. When you are close to the heliospheric current sheet, that messes up things, and then you loses the galvanicity, then you don't see this kind of secret.
But is it real common even, you know, like way up here, the field, I guess, blue is out or in or whatever it
There are
is, say it's
switchbacks
in.
here, yes.
There are some where
Yeah,
that's
so-
the red here.
Right, yeah, so you see little dots of red.
Yeah.
Right, if you look at what is it, Horbury 2018, where he
Yeah.
did Ulysses wind helios.
Yes, I think I have it here.
And he shows, yes, there are really tiny switchbacks at Ulysses and they get bigger and bigger.
So the fact that they stand out so much with solar probe is because we're so close to the sun.
It's
the
because we're
field-
so
Yeah.
close and just the VA is so large that you get a large enough fluctuation.
I don't have, oh yeah, here you go. So this is not the magnetic field, but these are the associated radial jets.
Mhm.
So at Ulysses, you have these little jets,
Yeah, yeah.
but then and so this is Helios, it's not Parker. And you have this much bigger.
Yeah.
Uh,
And that's
uh,
flow velocity. That's
That's the
not,
velocity.
that's the flow velocity, not the field strength. So that's really,
Yeah, but
that's
that's,
really pretty striking, actually, that you get these big rapid changes. So like these big blowout particles shooting way out really fast and, yeah, really quite striking. So, Any other questions? Yes.
Oh, this is one of way back near the beginning when you were doing, where you were showing the macroscopic and microscopic.
Yeah.
Equations. Is there any interaction with background radiation fields such as coronal X-ray emissions or?
As far as I know, really those are studied like test particles so that they are sparse enough not to affect globally. I haven't seen models that include that other than models with pickup ions, if anything.
No, I was just curious about.
Yeah.
You know, Compton scattering, inverse Compton scattering onto both the solar background spectrum, but also just the various structures that exist, high X-ray emission regions and low X-ray regions.
I'm not aware of models that include those like self-consistently.
Interesting, is the corona optically thick for the X-ray?
Well, I suppose you could have compact regions that second.
Well, okay, maybe we'll call it a wrap. So anyways, thank you very much for this. It's a very fascinating talk. So,
Thanks.
great, thank you, Anna.
Thank you.